Hello friends, welcome to my channel. Let's have a look at problem 988, smallest string starting from leaf. In this video, we're going to share some treatment based on traversal. This video is a follow-up for problem 124. So problem 124 is today's daily challenge problem. So in this video, first I'll read through the problem statement to digest the requirement, and then we look at the example, and finally we share the code and explain them line by line. First, let's look at the problem statement. So we are given the root of a binary tree, where each node has a value in the range 0 and 25, representing the letters A to Z. So we are required to return the lexicographically smallest string that starts at a leaf of this tree and ends at the root. So as a reminder, so any shorter prefix of a string is lexicographically smaller. For example, AB is lexicographically smaller than ABA. So here a leaf is a node that has no children. So with this done, let's look at the three examples here. So in the first example, actually we have 4 leaves. Therefore, we have 4 leaf to root string. So one is DBA and the other is EBA, and the other two are DCA and ECA. Because we want to find the lexicographically smallest one, so we compare the two strings starting with D. So the first one is DB and the second one is DC. So we are going to choose the DB one. Then go to the leaf root, so we get DBA. So this is the return for example 1. So similarly, we can look at example 2. So the 4 leaves are BDAC, so we choose this one. So we get ADZ. So with that done, so let's look at the constraints. First, the number of nodes in the tree is in the range given by the closed interval, so 1 and 8500. And the node value is in between 0 and 25, both ends inclusive. So because we have 26 lowercase characters. So as in the problem statement, so this problem statement indicates that the node values are actually characters, lowercase English characters from A to Z. So with that said, let's look at the coding. So this problem actually is almost identical to problem 124, but the difference is that, so here we are considering strings, and in problem 124 we consider root to leaf values, right? But here the order is slightly different, right? So we are considering leaf to root strings. So for strings, actually there's a natural, the natural order is lexicographical order. So this is actually very convenient for us to compare. So in the first version of the solution, I'm going to write with some redundancy just to understand the overall logic, and then we do a slight improvement of the code. So for convenience, I'm going to first get A, B, C up to Z. So this can be done by import, right? From string import ASCII lowercase. So I'm going to call it characters, give it an alias. So with that done, so what we can do is like this. So we get a table. So in just for convenience of check lookup, so you don't need to do this in general. So I character, for I can enumerate characters. So this is the preparation. So now I'm going to initialize a array. So the array will be store the leaf to root strings, right? And then we can start this one, and right, then we get the first element. That's the result. So in the first version, we are going to content ourselves with this sort of coding. So v1 get all the leaf to root strings, sort them, and return. So this is our boilerplate. So the casing is we do a traversal. So for this, because the number of node in the tree is at least one. So in other words, the tree is not a null tree. So we can do a traversal with iterative format. So here I'm going to store the strings. I'm going to store leaf to root strings. So here the string will be table, the corresponding root value, right? The root value. So this table maps the value, integer value or index to the corresponding characters. So this is the initialization for this stack. So now let's do this. So while s, first I'm going to get the node string, that is s pop. So because here we are using stack, you can see what we're going to do is depth first search or depth first traversal. But let me first finish this while loop part, and then you are going to see this the code. I will let it corresponding to in-order traversal. So if first, if not node left and not node right. So this means that the current node is already a leaf. So in this case, so we're going to append this string to the array. So this is the one case. So actually, it's also a check of leaf to root strings. So afterwards, so the complementary of this if is either node left or node right or both. So let's do a check. So here I'm going to first check node right. So I first append node right. So it's node right. And then because we want to compute leaf to root strings, I'm going to do the corresponding character first, append in the front, right? So this node right value, and then plus the pre-string. So we use this as a prefix each time. So this is for node right, and then let's do node left. So let me copy this part and then make some modification. In other words, I'm going to change the right to be left. And then this basically finishes the traversal. So if you ignore the second component in the tuple, so this while loop is nothing but in-order traversal. Notice that we put right in before left, right? So if you in general for this problem, actually the order node right, node left is not essential. But if you want to do in-order traversal specifically, we need to first put right and then left. So with that said, actually after this while loop, we are going to collect all the available leaf to root strings. Then we can do a sort. So sort this one. Then this will sort the array in a lexical small to large order. So what we are going to do is to return array 0. So here this array at least contains one element. The reason is that the root is not null. So this snippet of code forms its solution format to this problem. So before we do any comments, we can first do a check. Yeah, it passes the first example. Now let's look at the second example, not generic case. Yeah, it passes all the generic cases. So in this version of code, actually we waste a lot of space. For example, here we don't need to get all of them, and here so we did a sort. So let me copy this code, and then I'm going to change this one to be v1, and then let's use this one as v2. So for v2, we just do comparison and return. So here we keep this table, and then I'm going to set a result to be null. And then what I'm going to do is not use the append operation here, but what we do is to do a condition check. So if result, in other words, if we have already set result, then our result will be the mean of result, because this one represents a leaf to root string. So I'm going to reset the result variable to be the lexically smaller one. So this is the else condition is if result haven't set yet. In other words, we met our first root to leaf to root string. So we're going to set this result to be the string. So this actually forms another format. For sure, we need to delete this part and return the result stage. So in this version of code, actually we implicitly using the natural comparison order of strings in Python. So before we do any further comments, let's first do a check. Yeah, it passes one example. Now let's look at generic case. Yeah, it passes all the cases. So I guess it's almost it for this problem. And in this video, we presented a solution based on traversal. So here the traversal is in iterative format, and we give slightly different two slightly different formats with different space complexity. So almost the same, because the stack is all of the number of leaf nodes, the number of nodes in the tree. So they're almost similar. So because here we do sort, so sort is an O n log n algorithm. Here n will be the number of strings in the array. So, but in the second version, we change to be this comparison, right? So with that said, I guess that's about it. So you're welcome to make some extensions and writing the code in recursive format, for example. So that's it. Thank you.